All right, let's look at the topic indices. And I know that this is indices is one of the topics that are really, really important in mathematics. We use it to solve a lot of problems applied. That is, we use the principles and the method of indices in so many topics. So that's why it is very, very important. But there are some of them that we only solve it, but we don't understand the principles and the rules behind it. So that's the reasons why I want us to look at the topic indices. First is really relates to algebra expression where alphabet are used in solving or simplifying or evaluating some problems. So now let's start. Now, do you know that in indices we use alphabet in solving problems, and in it enables us to be able to solve some other topics and like standard form is not only in mathematics alone, and also like in physics, we use the principle of indices. But now let's look at some elementary aspects of indices whereby it be a bedrock for solving problem in indices. For example, we know about this addition of alphabets like A plus A. We say that A plus A is 2A. Now, the 2 is the coefficient of A, telling us that A and 2 added together. And if we have A plus A plus A, it simply means as 3A, telling us that 3 is the coefficient. That 3 means that A and 3 adding together. That's what it tells us. Now, this is addition of alphabets. It can also happen with B, it can also happen with C, it can also happen with D or even to Z. But now let's look at an example of 4A minus 3A is equals to, what it simply means here is that we will remove A, how many of them? 3 of them from A's that are 4. So if we remove 3 of A's from 4A, it will just remain only one A, and the answer would be A. But if we would have written 1A, but since it's just only 1, so no need of indicating the coefficient as 1. So we only write 1 as we just written here. So now I have been able to talk about um, addition of alphabet. Now look at this. If we have 3A plus 2A, we will say it is 5A, right? And this is the elementary aspect of algebra expression. But now let's look at this alphabet in another way, another calculation. For example, by calculating, for example, they give us A times A. Now, in this case, it's now going to be A raised to the power of 2. Now, this 2 is the power. It also the index, and it's also the exponent. So any of these words represents 2. This 2 tells us that A into 2 multiplies. Now, Let me go into this again. If we have A times A times A times A, it will give us A raised to the power of 4. Now, this 4 is the power, is also called the index, is also called the exponent. So, in that case, it's telling us that A into 4 multiplies. That is algebra expression. But now, this is an index. But a situation where we have more than one index in a particular value, for example, A raised to the power of 2 over 3, or A raised to the power of n m. The index are more than 1. Is no longer 1, like this is 2 and here is 2. So now, since index is more than 2, is more than 1, it is now called indices. It is now called indices. So when it is 1, we call it index. It's also index or exponent or power. But when it is more than 1, we call it indices. So indices is the plural form of index. I said that indices is the plural form of index. Then how did it plays its role in mathematics? So that's what we will really want to go in depth and discuss, and which will really help us to be able to solve all the problems in indices. Now, first, in mathematics or in life, everything have principles or rules. The same thing happens to mathematics, like indices. They have its own rules in each of them. Now let's look at how we can discuss each of the rules in indices, which are the principles. Without not you obeying the principles or the rules, you can never ever be able to solve it. So it's just like making someone to be your friend, to be happy with you, or like to stay with you. There are some certain things you will not want to do, and there are some certain things you would like to do in order for the person to be happy, like he's staying with you. So the same thing with indices. So now let's look at rule one. Rule one. Rule one. Very important. Says that a raised to the power of n times a raised to the power of n. I may not really want to go deeper and deeper into it. What it simply means is that the two base value, because they are the same, will still represent, one will represent itself as a, but the index now will undergo addition because they undergo multiplication, which now going to be n plus m. So they will plus, they will not times, they will not multiply, as because here is multiplied. So rather the index will add if two values undergo multiplication, their index will add. So for example, if we have a raised to the power of 3 times a raised to the power of 2, it simply means a raised to the power of 3 plus 2. And 3 plus 2 is 5. So that will be a raised to the power of 5. I know this is one of the most simplest rule or principles in indices. So I may not really want to go deep into it, but I actually want to just discuss this, which everybody understands and everybody knows about this. But now let's move to rule two. This is important. Let's move to rule 2. Now, in rule 2, states that a raised to the power of n divides by a raised to the power of n, right? Then in this case, it simply means that we have one a and n will subtract with n. So n will subtract from n. So that's what will happen. For example, we will have a raised to the power of 4 divided by a raised to the power of 3. A raised to the power of 3. So what will happen is that we will have it as a raised to the power of 4 minus 3, and then it's going to be a raised to the power of 1. But a raised to the power of 1 is a. So we have it as a. And this is very simple, and I know you understand this particular principle. But this is not where I'm really concerned about. But I want to use this to refresh your memory and everything about it. Now let's move on to the rule 3, which is very important too. The rule 3. Now, in the rule 3, it's very important. It says that a raised to the power of minus n minus n. Look at the rule 3. Now, this minus sign as the index and also the index as n, this minus sign will reciprocate the alphabet A or the number A, and then n will still remain the index of A. Now, this is what will happen. It will now become 1 all over A raised to the power of n. Now, at this case, a raised to the power of n is reciprocated, is upside down because of the minus sign. So the minus sign reciprocates a. That's what it simply means. For example, if we have a raised to the power of minus 2, what it means that this minus sign will reciprocate a, and it will be 1 all over a raised to the power of 2, which also in the expression will be 1 all over a times a. I'm just expressing it, but I will have stopped here. But now let's use a number in the place of a. For example, we have 2 raised to the power of minus 3. Look at this. And at this point, the minus sign becomes makes 2 to reciprocate. That turns upside down. So it's now going to be 1 all over 2 raised to the power of 3. And here in the expression, it simply means 1 all over 2 times 2 times 2. And 2 times 2 times 2 is 8. So we will have as 1 all over 8. I want you to look at the expression, and I want you to understand what happens here. The third principle is very important. This is where the whole thing comes from, and it's always confusing, and that's why I'm really concerned about this. Now, let's look at some other rules that may have relationship with this. Now, Looking at this and look at this very well. I want to use rule 4 and to compare with this rule 3. Now look at the rule 4. I want to play and I don't want to clean it. Now rule 4. Now rule 4, it's really my consent too. Now, if we have this, they give us this a raised to the power of 1 all over n. Look at this. This has nothing to do with this. But looking at it, it seems as if this has something to do with this. It has nothing to do with it. Now, in this case, this one is a fraction, but this one is not a fraction. But the fraction involves the whole value, the best. But this one is a fraction of the index, but it's a fraction of the whole number. And where it comes from is because of the minus sign reciprocating the number, the base. So, like in this, it's telling us that this n is the root of a and 1 is the index of the a. So, what will happen will be the n roots of a and 1 becomes its index. When we have a fraction of index, when we have an index that is in the ratio, so automatically one of the index will be the root of that number, and one of the index will be still remain as an index. The one that is the numerator will remain as an index. The one that's the denominator will become the root. And that's another principle. That is the rule 4 of the law of indices. Now, let me go back. As in this, if we have 2 raised to the power of minus 3, it simply means 1 all over 2 raised to the power of 3, and it simply means 1 all over 2 times 2 times 2. Right? Let's continue from here, which also lead us to 1 all over 8, right, as the answer. But let's look at this, for example. So if we have a value like this, we have 8 raised to the power of 1 over 3, which 8 represents a, and 1 still represents 1, and 3 represents n. So it will now be the n root, and the n is what? 3 of 8. This is what that will happen. And we are going to look for a value. What it simply means, the 3 root of 8 simply means the value that when it multiplies itself 3 times, it will give us 8. And that value is what? 2. And the 3 root of 8 is what? 2. So if you can look at the expression of this and this, it have nothing to do with each other. But most at times, we always confuse with rule 3 and rule 4. So this is what I really want to let you understand more. In case you encounter most of these problems like this, you will know how to handle it. But let's move a bit further than this by applying it. But we have some related rules that relates to this than this, which we can also see on how we can solve it. Now, let's look at rule 5. I want to use this space to look at rule 5. Okay, let's use here for rule 5. Now, rule 5. Now, in rule 5, we can have a raised to the power of n over m. I don't know if it's too small or we have n over m. Now, it's still the same principle will still play. The m, which is the numerator, remains an index to a, but m becomes the root, m root of a. So we will have this as this m root of a raised to the power of n. But in this case, we can write it in two different ways, or it can be as this m root of a raised to the power of n, or like this. Now, in this one, it simply means n will be simplified first before m will be simplified. But in this one means that m will be simplified with a first before n will be simplified. So you're looking at this, there are ways in which this can be used and this can also be used. So this method has more relationship with this than with this. So let's see how this plays out. And I will solve using this method and also solve the problem using this method. Now let's see how we can solve, what kind of problem we will use this and what kind of problem we will use this. It is very, very important understanding when to use this and when to use this, and when not to use this and when not to use this. Now let's go ahead and see how we can solve problem on this. Now it's a continuation of the rule 5, and I want to use it here. Now, if we have 4 raised to the power of 2 over 3, okay, let me not use 4 raised to the power of 2 over 3. Let me use 4 raised to the power of 3 over 2. Let's use this. Remember the method, the formula, the equation. Look at it, it resembles this. So what happened here is the 2 becomes the 2 root of 4, right? And at that point, in this case, because 2 can simplify 4, since 2 can simplify 4, so therefore, and 3 cannot. So what happened is, we will first of all put the bracket, and then we will now write 3, which this method is used. If you can see it, it's very simple. But if we use the other way first, by saying 2 of 4 of 3, we may have, and the tendency of getting a value that would be get a square root may not be there. 4 times 4 is 16. 16 times 4, right? So we know what it is going to be, 64. But there's still possibility of getting the value. So in that one, in this particular one, we can use the two methods. But we can use this and also we can use this. So now, but looking at this first, we can use this method first by solving it. Now look at this. Now, we will now simplify the square root of 4, which is what? 2. And we will now have as 2 raised to the power of 3. So which will now, the result going to be 2 times 2 in the expression times 2. And the answer is what? 8. As simple as that. But now let's look at it in the other aspect where we have the root 2 of 4 raised to the power of 3. So now in the expression, we will now have the root 2 of 4 times 4, sorry, coming, it's so tiny. Now we will have 4 times 4 times 4. You know, 4 times 4 is 16, and 16 times 4. Let's see what will it give to us. Let's be sure. We have 4 times 4 times 4 is equal to 64. So we will now have it to be the square root of 64. And the square root of 64 is 8, exactly as this. Now, we are able to use the both methods to solve and still get the same answer. But there are situations where one can be used and the other can't be used. I will still deal with that. But one of the method can be used and one can't be used. I will also go into it and then we'll discuss it at length. But I really want you to understand these two clearly. Now let's go on to see how we can solve that. I clean this. Still the rule 5. Now look at this. Very, very important. If we have 8 raised to the power of 2 over 3, for example, which is similar, the same thing as this, as the rule 5. So what it simply means is that we will have the 3 roots of 8 close bracket raised to the power of 2. Right. We can have this. But at this point, the same thing can play out. For example, we now find this, we will now have this 3 root of 8 is 2 raised to the power of 2, and it's now going to be 2 times 2, and the answer will be 4. Good. Now let's look at it in the other way, which is now going to be the 3 root of 8 raised to the power of 2. The same method. Look at this. So now we will now have the 3 roots of 8 times 8, and this will lead us to the 3 roots of 64. So we think of a value that when it's simplified, we multiply it into 3, it will give us 64, and that value is 4. So the answer will be 4. So you can see the methods used here and the methods used here. It still goes the same way. But let's look at another one. I'm explaining another one, still using the same value, but I'll change the numerator and the denominator. Look at this. If we have 3 over 2, if we have 3 over 2, what do you think will really happen? Can it be solved? That is where the whole things play out. Can it be solved? Now, what happened here is now going to be the 2 roots of 8, right? Either raised to the power of 3 or the 2 roots of 8 raised to the power of 3. So any of these goes. But at this point, you can't simplify this first before this. It will give you a decimal values. So automatically, this one is completely cancelled out. But now let's see for this. The 3 root of 8 will be 8 times 8 times 8. So we have 8 times 8 times 8, and it's equals to 512. So we will now have, right, to be the square root, we now have the square root of 512. Now, let's see from here. So if you can see at this point, in this case, if we want to express this, we will see him have it as 1602 as the value, but still have a decimal value too. But where I'm coming from, if you can see from this one, there's no how we can start the expression here. But here we can start the expression to some extent, which will lead us to 16 root 2. But now let's look at it in another angle, another questions, another value. So I'm painting this. If we have 4 over 2 over 3, now in the expression, we now have root 3 of 4 of 2. This really explains what I want to do. You know, at this point, you can't simplify this. You cannot simplify it, but rather, these other methods have a play in it, which is now going to be 3 roots of 4 raised to the power of 2. Now, at this point, you can now express it by saying it's going to be 3 roots of 4 times 4, and that will lead us to 3 roots of 16. So we look for a value which is now the answer you know will be 2 root 2. But and then at the end of it, it comes in the decimal value. But this can be expressed to some extent as compared to this where we can start, because here we must start with the root 3 being simplified 4 before coming to the index. But here we first of all start with the index before coming to the root. So it depends on where and depends on the value. So that is why the two methods are really, really important. So I'll now move to the next rule, and we also look at some of the principles behind. Okay, I clean this. Now let's go to rule 5. Rule 6. Rule 6. Rule 6. Very, very important. Now, the similar value of this and related with rule 3. Now we have a raised to the power of minus 1 all over n. A raised to the power of minus 1 all over n. There are two rules in one problem. We have rule 3 and we also have rule 4 in this particular one. First, the rule 3 is the index, is the minus sign, which is what the reciprocal of the value, while this one is the root of a. So first, we will now have 1 all over a raised to the power 1 all over n. So now this was rule 3, playing its rules, but now this is rule 4, which we have not yet expressed it, which need to be expressed, and now going to be 1 all over the n root of a raised to the power of 1, which is also going to be n root of a. So it's the combination of two rules playing in one, and which is rule 6. So it's what we really need to understand, that the minus sign is the reciprocal of all of it, and this plays its same rule. You still need to express it. So for example, if we have 4 raised to the power of minus 1 over 2, I think the number is too small that maybe you cannot see. We have 4 raised to the power of minus 1 all over 2. Now, the minus sign you make 4 will reciprocate 4, and that will be 1 all over 4 raised to the power 1 all over 2. This is the rule 4, while this is rule 3. So in the expression, is going to be 1 all over 2 root 4. And we will now have 1 all over the 2 root 4 is 2. And the answer will be what? 0.5. So I want you to look at the expression. It relates to 4 and also relates to 3 and even rule 5. Now let's look at the one that relates to rule 3, rule 4, rule 5, and rule 6. It's really, really what we are interested in. Okay, let's look at it together. Now, rule 7. Now, in rule 7, we have, for example, a raised to the power of minus n over m. You see, rule 5 is here, and rule 3 is also here. So it's a combination of two rules playing out in just one question, which it is in rule 7. So the first thing is that the minus sign will now reciprocate a, and n over m will still remain as its index. Now that will now show another rule entirely, where it will also be simplified. So we will now have 1 all over a raised to the power of n over m. And that is the expression. Now, this 1 over is not for n over m, but for a. Now, in the expression, now this is another rule which was rule 5. So rule 5 will play its own role by expressing itself. That 1 over will still remain as a reciprocal of the m root of a raised to the power of n. So this will be the expression, or 1 all over the m root, right, of a raised to the power of n. Any of these two really goes for it. So this is the exact expression I really want to have to show to you. You see, the first one was rule 3 being expressed, and the second one is rule 5 being expressed. Now let's see how this problem can be solved. For example, if we have 8 raised to the power of minus 2 over 3, there is a minus sign. So because of the minus sign, a will be reciprocated, which now going to be 1 all over 8 raised to the power of 2 over 3. Now in the continuation, now this is rule 5. We will express it, which now going to be 1 all over 3 roots of 8 raised to the power of 2. So now that will be 1 all over, by expressing it here, will be 2 raised to the power of 2. And it will now be 1 all over 2 times 2, and it's equals to 1 all over 4. And we can now say it's 0.25. So this is the way in which this rule can be expressed. And it is very, very important for every student to understand as the basics of mathematics. And it's really, really interesting to know more about this and to also use it to solve so many problems. But if you can see from the questions, the exercises that you will encounter in indices, some maybe more of this. Can use this like two of it, three of it, and also in the as a numerator and also as a denominator, and you'll be asked to simplify some, like three of it will be multiplied, two of it being multiplied in as a numerator, and two can be in the denominator in multiplication and also at the same time dividing. Then they'll ask you to simplify it. You look at it as if it's most complicated, and some of them will be on the fraction in ratio and at the same time have another index. So by the time you understand these simple principles, I really believe you can easily solve any problem in indices. But we are still going to move a bit further to see how we can solve some few complicated questions in indices by using these principles. But I don't want to extend more than these principles, but I only want to add only just one principle to this principle. And after having that principle expressing it, then we will see on how we can solve at least two or three complicated questions in indices. All right, now let's go on. I can make that rule 8, but most textbooks will say this rule will be rule 4, some say it's rule 3, some say it's rule 5. But I want to make it rule 8 because there are some rules here that were so important to me than that rule. Now, looking at this, remember this rule that says that a raised to the power of n divides a raised to the power of m. It simply means a raised to the power of n minus m. But what if the magnitude of this index is the same magnitude of this index? What will happen? Let's look at this, and we can call it rule 8. Rule 8. Now, if we have a raised to the power of n divides a raised to the power of n again, so that will lead us to a raised to the power of n minus n, and it's going to be a raised to the power of 0. But remember that these two values undergoes division, so which we can say as a raised to the power of n divides a raised to the power of n. That's what it means. So, and a raised to the power of n goes to a raised to the power of n how many times? 1. So the answer is what? 1. So we can now also use the two results by saying that a raised to the power of 0 is equals to 1. That is what it means. And this is our rule 8. This is also very, very important for us to understand why it's so. So in that case, any value raised to the power of 0 is equals to 1. If we have 1000 raised to the power of 0, the answer is what? 1. If we have 380,000 raised to the power of 0, the answer is equals to 1. So any number raised to the power of 0, the answer is 1. So I want you to note this, and let's see how we can just solve some few complicated questions in indices. All right, let's look at these three questions. The first one is 18 over 32 raised to the power of minus 3 over 2. As you can see, this is in my own rule. This is rule 3, and this is rule 5 playing out. So by solving the number 1 question, we bring down the question 18 over 32 close brackets of minus 3 over 2. Now, because of the minus sign, it reciprocates, and that will now be 1 all over 18 over 32 close bracket of 3 over 2. Now, this is rule 5. So, we will now have 1 all over the 2 roots of 18 over 32 of 3. But what really happens here is that first you will look at it and how is it possible for this problem to be solved? So we will now say 2 goes to this, it gives us 9, and goes here, it gives us 16. So now what we will now have will be 1 all over the 2 roots of 9 over 16 of raised to the power of 3. So now we will have 1 all over the 2 roots of 9 is 3, and the 2 root of 16 is 4 raised to the power of 3, which it simply means 1 all over 3 raised to the power of 3 all over 4 raised to the power of 3. That's what it means, and it will now result to 1 all over 27 over 64. Remember, this is a fraction, this is a whole number. So this becomes a fraction by saying 1 all over 1 divided by 27 over 64, which this multiplies with this, and this multiplies with this, and we now have 1 times 64 divided by 1 times 27, and the answer will be 64 over 27. This is the expression for the question, which is a bit more simple to handle. So if you can see, it is the rule 3 and the rule 5 that is used. But what makes it a bit more complicated is because the values are in fraction. So it makes it as if it's more hard to handle. But by the time you understand this, you go over it and then you solve it and you arrive at your answer as I'm doing it. So, okay, now let's move on to the next question, number 2. Question number 2. Let's see how question number 2 can be solved. Is 75 a raised to the power of 2, b raised to the power of minus 2, all over 5 a raised to the power of 3, b raised to the power of minus 3. Now, looking at this, first is that you now say 5 goes to 75 how many times? That's the first thing you do. 5 goes to 75 how many times? Now let's see from a calculator how many times will 75 divided by 5 will give us 15. So now you will now have a 15, right? Then remember that when two values are dividing, their index will subtract. So now this and this divides. A raised to the power of 2 will divide with a raised to the power of 3, which is now going to be a raised to the power of 2 minus 3 from the law of indices, that whenever they divide, their index will subtract. The next value was b. Now raise to the power of minus 2. And here we'll do what? Subtract. Minus of minus 3. That is what is going to be. Then in our continuation, we will have 15a raised to the power of 2 minus 3 will give us minus 1. And here we have b raised to the power of minus 2. Minus minus is plus. We have plus 3. So that will result to be 15 raised to the power of a raised to the power of minus 1. I mean 15 a raised to the power of minus 1, b raised to the power of what? 1, which the result would be 15 a raised to the power of minus 1, b as the answer. Then if we want to express it again from a, remember a is another law of indices, which we now have is as this. From the expression, we will now have it as this 15 into, from the law of indices, the minus becomes a reciprocal as 1 all over a of b, which will now result to be 15b over a. This will be the correct answer. So this is very, very important for us to understand. And I believe by following the rule, I'm able to solve to this extent. Now let's see the last one, which is very, very interesting. And I really want us to get along with it and understand it. Now, let's look at the number 3. It says the two roots of 1, 2, 5 raised to the power of 2 close bracket of minus 1 over 3. Looking at it, you yourself will say, how? This is more complicated. It affects you. Looking at that question is very hard to handle. But first, we have a rule here as rule 1. We have the second one, rule 3. And we have the third one, rule 4. And this is also a rule 2. It's also rule 4. So about 3 rules are applied in one question. Then how can we solve this? Let's see how we can express this. So now, first, what we're going to do is that we look at the reciprocal, which is the minus sign, which now going to be the root of 1 all over, open bracket, 1, 2, 5 raised to the power of 2 of 1 over 3. That's how it is. So, in the expression, if there's another rule here plays, which that rule, I did not discuss it. I did not explain the rule, which means that the two index will multiply. So if we multiply the two index, now we will now have the root of 1 all over of 1, 2, 5 of 2 times 1 over 3. This is what will happen. And we will now have the root of 1 all over 1, 2, 5 of 2 over 3. So you can see the rule plays out. So now, in the continuation, we will now have, and I think it's very tiny to be seen. Okay? Here is 2 of times 1 over 3 3, right? Okay, it's a bit clearly seen. So, which now, there's a rule here, which is now going to give us. Now, we can express it in that way as 1 all over the 3 roots of 125, right? Of 2. If you can see it. So, that leads us to be 1 all over. The 3 root of 125 is 5 raised to the power of 2. And that will give us root of 1 all over 5 times 5. And that will lead us to the root of 1 all over 25. And the root of 1 over 25 will be 1 over 5. And the answer will be what? 0.2. That's how we get the answer to the expression. So I stop there, and from it, I really believe you understand what I'm doing, and you can equally repeat studying it and more and more. So I want you to subscribe, like, and share my YouTube channel. Thank you.